And what I'll do, we'll start with on the whiteboard. So let me get the screen share up there. And I will then, you probably can't tell what I'm doing now, but I'm going to be moving taskbars out of the whiteboard so I can write on it and read what I'm writing. You could still see it, but I wouldn't be able to see it, so I wouldn't know how terrible it looked. Move this one out of the way because you don't see what I'm doing. You probably just see the arrow going across the screen, right? Okay. Yeah, but you don't see the taskbar that I was moving. Okay. All right. And then I'm moving the whiteboard. I don't know if you can detect its motion. So I get the maximum amount of white space. Okay. All right. The last time, so any questions about linear algebra? We've been talking about other, oh, wait. Here comes James. Okay, let me get him in. Or do we want him in today? I don't know. What you think? You think we ought to let him in? Yeah, let's do it. Okay. All right. James is still connecting to audio, so I'll hold off a bit. So, hope James can hear me now, right? All right, good deal. We got Aaliyah and you here so far, so we got half the class. Aaliyah and I had been talking about things before you got here, so we're ready to start now. Do you have any questions before we get started? Okay. There was a question in my last class, and I think I need to address it here too. I'm sort of embarrassed by it, but I have been trying my best to catch up with printing all the stuff that's been coming in. And this isn't quite accurate, but this is mostly what came in that I was able to print over the weekend. Not all that came in over the weekend, but it's stuff that I was able to print. Now, I was gone for a good part of the weekend, and I didn't have printer access, I didn't have internet access. I was hoping to get more grading done of stuff I had printed than what I got done. I got a fair amount done, but I didn't get enough done. The problem was we had really nice weather, so I was outside working just about the entire time. So I didn't have a lot of time to do grading, but I did get some grading done over the weekend, long weekend. But yesterday we came back late Sunday, and so yesterday I spent most of the day printing out the stuff that had come in either over the weekend when I couldn't print, or in previous weeks that I hadn't been able to print in those times. And here's part of my sad song about why I couldn't. We are in the middle of changing from the old course management, well, not just the college management system. We had been using an ancient program called Alliant. We had used that ever since Western State Tech was merged with Lawson, and Lawson had been using it I don't know how many years before. It was really not a very good old program, but it's what we used. It's called the Alliant program. Well, the new administration down in Montgomery has decided everybody in the whole system is going to this one new package called Banner. And that's what the administrators, oh, here comes Ricky. So Ricky is here, or coming here anyway. So that gives us 3 out of 4. So that's excellent. Okay. If only we can get your manual here, we'll have perfect attendance again. So anyway, and Ricky sounds like she's on board now, so that's good. Ricky, you may have heard this on the first time. I can't remember when you came in the last class, but we are changing to a brand new management system called Banner, and that's been occupying the administration basically all summer. Okay, and now it's going to filter down to faculty and students, and we had some training last week, and that ate a bunch of the time that I had to grade and to print stuff, and that's one reason I got behind. Another reason, and we've been having those little spurts of training here and there and meetings and other things, and lots of requests from the administrators about, you know, who's going to be in charge of what classes and that kind of stuff, and just tons and tons and tons of emails. So that's why I didn't have all the things printed that I needed to have printed, so I could get everything graded that I needed to have graded, so then I could get grades on Blackboard that I needed to put on Blackboard. So it's all a domino effect, and it's continuing this week. In fact, this week they've designated as advising week. So I have to do extra advising hours this week. Well, so far no one signed up for my advising hours, so I don't have to be occupied, but it could be that the next 2 days, Wednesday and Thursday, I may lose up to 4 hours of it, what I would have as office hours as advising hours. So it never gets over, it seems like. So anyway, I'm behind, and it feels like way behind, but I'm getting caught up gradually with first printing, then grading, and then ultimately to get the grades on Blackboard. So I'm doing my best to get that done, but I just keep getting interrupted by either meetings or requirements to send stuff to somebody or something else. I just was reading in between classes a very long email from the vice president about something I never could get to the punchline. It just went on and on and on, but I had to stop and get the class started. So that's where I'm sitting, but hopefully this week I can take advantage of whatever time I've got and try to get as much done as I can. So if you're seeing things out there, that's why. I've been trying to email you when I print stuff, and but you won't know when I get it graded finally until you see the grade in Blackboard, and that's yet another step down the road. So I'll try to get it caught up as much as I can today, because I don't know what the rest of the week's going to be like. So anyway, that's my sad, sad song. So let's move on to where we left off last time. We had talked about, we're in Chapter 3, Determinants, the last section in Chapter 3, which is 3.4, Applications of Determinants, and we are on Example 1, finding the adjoint of a square matrix. Okay, and I'll go back and review what an adjoint is in just a minute. Let me write down what the matrix is. Okay, get my pad in place and see if I can get it written. So here's matrix A, a good old 3 by 3. -1, 3, 2, 0, -2, 1, 1, 0, -2. Now that's just a square 3 by 3 matrix. Okay, find the adjoint of that matrix. Okay, now let me go back and remind you what the adjoint is. Okay, there's 2 steps to the adjoint. First step, find the cofactor of each one of these positions here, the cofactor. Okay, but then once we find the cofactors, transpose the set of cofactors, the matrix of cofactors. So when you have the transpose of the matrix of cofactors, that's the adjoint. Now, my question to you, do you want to try to do that in 1 step or 2 steps? Find the set of cofactors, the matrix of cofactors first, and then transpose, or do you think we can find the matrix of cofactors and transpose as we go? That's my question to you. What's your answer? As we go. Okay, so let's see if we can come up with the adjoint. Okay, the adjoint ADG, ADJ of matrix A. Okay, it's also going to be a 3 by 3. Okay, now this first element here is going to be the cofactor of this element here, the -1. So you could wipe out the first row and first column and answer my question, what is the sign of that position where -1 is? That's a positive sign. So when we find the cofactor, which is the minor of that, which would be what? No. The minor of it is you wipe out this row. I was not going to do this because then I have to erase my wipeout. And that column, and it's the plus of that, and it's the minor. What is the determinant of that minor? Yes. 4. Okay. So this is going to be, that first entry is going to be a 4. Okay. Oh, okay. Well, the minor is the determinant of what's left. Okay. Yeah. That's why I didn't say it until at the end when I was trying to, yeah, focus on it. Okay. Now I've got to go through and sometimes I have the pad in my lap and sometimes I have it on the keyboard. I try not to have it on the keyboard because it punches keys and makes noises. Okay, so I need to wipe out that construction line, this construction line, that construction line right there. This is so aggravating. It changes my eraser into a selection and I don't know why. And then these two, okay, so there's back to the original matrix. So now you said you wanted to play as you go, right? So what we're going to do, you tell me what position you want to do next. Pick out the number in this matrix that you want to do next. Do you want to do this position, the 1, 2 position, or the 2, 1 position, or any other position? I don't really care. Other than 1, 1, we've already done 1, 1. The 2, 1. So that's the 0 right down here, right? Okay. Now don't worry that that's a 0. We're not multiplying it by anything. We want to know the sign of this position though. And what is it? It's going to be a minus. Okay. Now hang on to that thought. This position here is going to translate once we do the cofactor of this position here. It's going to wind up right here. Do you see that? Because then we're going to transpose. And you want to do 2 steps at once, right? You're the one who said it, right? Okay. All right. So it's going to go there. Don't worry that it's a 0, okay? But it's going to be a minus. So whatever the cofactor is, the minor of this position is, we're going to negate it. So I'll go and draw them in. We'll wipe out that row and wipe out that column and do the determinant that's left. And what do you get? Say again? It's a -6, but because that is a negative position, that becomes a +6, but we put it up here because we're going to transpose, swapping row and column. Okay? Yeah, okay. Now, ready for the next one. Okay, let me first erase my lines here. You want to do 3, 1? Okay, I'll just wipe out that one. And then since we're going to do 3, 1, I'll wipe out, I already had column 1, wiped out row 3. And since this is going to be 3, 1 down here, it's going to be 1, 3 up here. So this is where it's going to go. Now, first thing we ask ourselves, what's the sign of this position down here? Positive. So let's do the matrix, the determinant here. What do you get? Okay, you're right. That would be a 7, and it's a plus position, so we have a 7 right here. All right, so there's the cofactor there, and they got it right in the book too. Good for them. All right, now I've got to do more erasing. If I can get the pen over here to pick up the eraser, I need to erase that construction line and this construction line and get my draw back here. All right, do I guess you want to move to 1, 2? Okay, well that's going to correspond to 2, 1 over here. And the first thing we ask about 1, 2, we're going to wipe out row 1 and column 2. And what is the sign of that position where that 3 was? Negative. Well, let's do the determinant and see what we get. Okay, so that winds up just being a 1 there. Okay, the book got it right. Good for them. All right, so I take it next that we probably want to 2, 2, which will be wipe out that construction line. And the good thing about 2, 2, it's also going to be 2, 2. You just reverse row and column, and it's still 2, 2. So let's wipe out that one. Well, what's the sign of this position? Plus, a positive. Okay, everything on the main diagonal is positive. So yeah, that's positive. And then the determinant here would be, yeah, 2 minus 2 is 0. Okay, a big old 0 in the center here. Okay, and that's what they got to. Good for them. Okay, I take it probably next we want to move to the, yeah, if I can get my eraser to erase, 3, 2. We've already got column 2 erased there, so let's erase. Wait. This drives me nuts. Okay. We need to, okay. It's the 3, 2, it's the 2, 3 here, which is the 3, 2 there, so that's going to wipe out that line. Okay. It's doing 2 steps at once. Okay. Now don't worry, that's a 0 there. That isn't even entering the picture. All we're interested in is the sign of that position. And what is that? Negative. So let's do the determinant and see what we get. Positive 1, you're right. And 3, 2 there corresponds to 2, 3 here, and that's a 1. I didn't put a line under it, so let's just move on. All right, next we'll move to this position, so I'll put the line under it this time. And that's going to be the 3, 1 here, so we'll be doing the 1, 3 there, which means I've got to erase both lines. Okay. Okay, and this time we'll wipe out the 1, 3 position here. Now what's the sign of this position? That's a plus, that's a positive sign. What's the determinant? Okay, remember this is up diagonal that you just did here, and that would be minus a minus 2, right? Yeah, all these minuses are only there to trip you up. You know, you realize that. That's the whole all-purpose in life of a minus sign, is to trip you up as much as possible. Okay, so we got a 2 in that position, which agrees with what the book has. Okay, Now we'll go to our last position here, which is not last, but close to it. This is the 3-2 on the adjoint, which means it would be the 2-3 on the main, on the first thing. So that means we'll, let's see, I just said it, 2-3 there makes it the 3-2 here. No, 3-2 there makes it the 2-3 here. That's what I was trying to say. Okay, so I'll wipe out that one and do the 2-3 here. Second row, third column to make the third row second column here. What's the sign of this position here? Negative. What's your determinant? Got it. So the adjoint position there would be a 3, and that's what they got. So the very last one here, and fortunately this one is going to be similar because it is your on the diagonal, and those are always the same. You don't have any transposing to do, so it'll be the 3-3 position in both of them. Okay. And what's the sign of that position? Positive. And what's your determinant? Again? Say again? How did you get that? Ah, yes, 2. Okay. So that will be a 2 if I can get it over here to write it. Okay, so there's the adjoint of that matrix. Boy, what a pain. Okay, but doable. Okay. Now, why are we even messing with something called an adjoint? What is the purpose for it? Is there any reason besides just another exercise to do? Well, the top of page 135 tells us the adjoint of a matrix A can be useful for finding the inverse of A as shown in the next theorem. And here's what that theorem says. If A is an n by n matrix, meaning it's square, which means it does have a determinant, and not only is it square, but it's also invertible. That means it does have an inverse. Okay. Now, of course, if it wasn't square, it can't be invertible. Okay. If it's invertible, it's got to be squares. Now, if that's the case, A is a n by n invertible matrix. That implies that the inverse of A, because you know that exists, it's an invertible matrix. So it has an inverse. And that inverse is going to be 1 over the determinant of A, this is looking familiar, isn't it, times the adjoint of A. And sure enough, that's exactly what we did when we had a 2 by 2, if you remember. Okay? If you remember, when we're finding the determinant of an adjoint of a 2 by 2 matrix, that's real easy. Down the product of the down diagonal minus the product of the up diagonal. Okay? 2 by 2. We've been doing it all along. Okay? That was, and we did 1 over the determinant times. Now what did we do to that 2 by 2? You took the 2-2 entry and moved it to the 1-1 and moved 1-1 down to 2-2. Well, guess what? The adjoint of a 2-2 matrix for the 1-1 position is 2-2 position. You just move it up there, and you do the same thing moving the 1-1 down to 2-2. And then the next thing we did was change the signs of the other 2 positions. Well, what was that? The the sign of the 1, 2 position is a negative, and its adjoint was the position below it. I mean, in the 2, 1 position. So the new 2, 1 would have been the opposite of what it was, but because you transpose, it moves up to the 1, 2. So yeah, you just change the signs of the other two, okay? Because that's what you did when their adjoint was across from each other, but then when you transpose, and they're negative because the cofactor, that's a negative position, so it changes the signs, but leaves them right where they are, okay? So sure enough, that worked. It works for any size matrix, except it's a lot harder to do. You're not just changing signs and swapping, you're having to actually calculate the adjoint, okay? But it's 1 over the inverse, 1 over the determinant is the beginning. Now, does that look any easier? Not at all to me, okay? Not at all to me. Unless, of course, you have a computer doing all this for you and you needed to get all that information for some other reason, then perhaps that would be one way to do an inverse, okay? But that is a definition, okay? Now, they do a little proof here. I say a little proof. It takes almost half a page to do that proof, and sure enough, you wind up that's the case. And the remark over on the side is exactly what I said. If A was just a 2 by 2 matrix, then the adjoint of the 1, 1 position is the 2, 2 position. So it goes there. And the adjoint of the 2, 2 position is the 1, 1 position. It goes there. Now, because when you transpose, those don't move, okay? So you just swap the positions. But when you do the 1, 2 position, its adjoint, it's a negative position here, and the value of the cofactor is that position down here at the 2, 1 position, so it becomes a minus. But when you and then you would transpose it, you wind up just changing its sign, is what the bottom line is. So anyway, you reverse the main diagonal elements and you transpose and you negate the other two, and that's exactly what we did. So let's do example 2. And example 2, thank you very much, book, Mr. Larson, Dr. Larson, whatever your name is. It says use the adjoint of A, and look, folks, at what A is. A is the same A we just had. So what I'm going to do is take eraser and wipe out my construction lines there, okay? We want to take that A, use its adjoint, which we found right here. So I think what I'll do is wipe out the construction. No, this is such a pain in the neck. Okay, erase that one, erase that one, erase that one, and that one, and that one, that one, that one, and that. I got them all erased. I'm so proud of myself. Okay. Okay, we'll use the adjoint we already had, where A was the very same A, to find A inverse. Okay, now how do we do that? We use this result here. All we need is 1 over the determinant of A. So the only thing we have yet to do, let me get my eraser back. I forgot to erase the one thing we need. Okay. All right. We don't need this part anymore. But this is what your inverse is going to be. So really the only thing we need here is to find what the determinant of A is. So let's do that. The determinant of -1, 3, 2, 0, -2, 1, 1, 0, -2. Now, I ask you this, sort of a rhetorical question, but it really is more than that. Which method would you like to do? Okay, we can expand this like we usually do 3x3s, and that's going to be fairly easy to do. Or we can do maybe a couple of row reductions or column reductions here, get a row of all zeros and or a column of all zeros, and then that's going to be pretty easy to do. So which would you rather do? Expand the 3x3 to do our old technique for that, or do you want to try to do a row reduction or column reduction to get more zeros in here? You choose. We can do it both ways if you wish, but choose one way to do first. Do the expansion? Okay, we certainly can do that. All right. And with expansion you mean wiping out this and repeating the first two columns, right? Okay. So the first column is -1, 0, 1. Second column is 3, -2, and 0. Now, I'm going to put the bar there, though you know this isn't truly a matrix, okay? Now, let's do the down diagonal here, and that's going to give you what? -4. Do this down diagonal, and what do you get? Got it. Do this diagonal, and I think I can almost do that myself. 0. Okay, so I'm going to wipe out my, if I can get my pen to show up, there it is. Okay, wipe out these construction lines because now they're more in the way than they're useful. We've already gotten our use out of them. Okay, now let's do our up diagonals. Remember, we have to negate these, and what would that be? +4. This one would be, this one would be. Okay, so what do we get as our determinant? 3. Okay, because the -4 and +4 add to 0. Okay, so we have a determinant, and now I think we're ready to go. The inverse of this matrix, A, is going to be 1/3 times that. So let's just do the 1/3 of every one of those elements. Okay, so it would be 4/3, 2, 7/3, 1/3, 0, 1/3, 2/3, 1, and 2/3. Now, since we had already found the adjoint, that made this a piece of cake because finding the determinant wasn't bad. So it was real easy. That part was far easier than doing a Gauss-Jordan elimination, of the matrix adjoined with the identity matrix, and doing that. But that whole process of getting that adjoint, to me, was harder than doing the Gauss-Jordan elimination. Okay, so, but if you had the adjoint already, for some reason, then doing this would have been really, really easy to do. Sorry. Goodness gracious. Got something stuck in my throat. I was eating a few almonds between classes. I think a piece of the husk must have come out and gone down the wrong pipe. All right, let's see how the book did. They got 4/3, 2 7/3, 1/3, 0 1/3, and 2/3, 1 2/3. Got it. Good for them. So that's one application of a determinant. It can be used, not claiming it's going to be an easy use, but it certainly can be used to find the inverse of a matrix. And we already knew for a 2x2 it's the easiest way to go. So, but 2x2 determinants are really easy too. So that was it. So now we move to a second application. And this application is called Cramer's rule. Okay? And this was, if my memory's correct, it may be the first place that I ever heard of a determinant. For some reason, the way they used to teach systems of equations, they decided to introduce determinants and have you do it this way. And it certainly works. Okay? Now, the lead up to why it works is somewhat of a real big pain in the neck or some other body part. Okay? But let's go back to a simple 2x2 matrix, except it's not so simple. We're going to use letters rather than numbers for our coefficients. Okay, so we'll use A11 times x1 plus A12, exactly the same identity we would use, times x2 is equal to some B1. Okay, and then we'll do an A21 times x sub 1 plus A sub 2 times x sub 2, and we would have this be that second constant be 2. All right, now, and I apologize again for this. This is also sort of some of the thirst issue. We were out of town this weekend. My wife's family had a place up in Smith Lake, very remote, and when her parents decided to consolidate all their properties so they could build their retirement home, they told us we were the ones without children, the only one of their three kids who didn't have kids, so therefore we needed to buy the lake place so they could build their retirement home. So we did. So now we're in charge of maintaining the lake place, and so we went up there to do a bunch of work. Had a great weekend for doing work, and that's one reason I couldn't get as many papers graded, because we didn't have any rain to speak of during the day when I would have been able to grade. So I wound up working all day and being completely out of energy in the evening. But in the process of working up there, I got eaten up with chiggers. Okay, so the only way I've been able to sleep at night is in the taking Benadryl. It supposedly dries up and stops the itching. Basically, it knocks me out. Benadryl just wipes me completely slick, but it also dries me out completely. So that's why I'm always drinking now and doing other things, and my eyes are so dry. That's why I had to take my glasses off and try to get a few tears to work up. Sorry about that. You don't want to hear the story of my life here. But anyway, that's my sad song. Okay, now, I don't know if you remember what the technique was for solving a 2x2 matrix like this. Okay, 2x2 systems of equations. Back before we knew anything about matrices or anything else, here's what we would do. We used the process they call elimination by addition. Okay, and what we did to eliminate was multiply one of these equations by something to let's just start with the x2. We want to eliminate the x2. So let's multiply the top row by A22. The top equation by A22. Be so much easier if we had numbers. Now, what we would then have to do is multiply the bottom equation by the negative of A12. Okay? Because you see, if we do this, that new top equation becomes A11, oops, got too quick on the draw here. I don't draw very well at all. Okay, A11 A22 times x1 plus A12, yuck, it'll go away in a minute. This pen is so jumpy. Okay, A12 A22, and that's equal to A22 times B1. Agreed? Now, second row we're multiplying by negative of A12, so that would make it a negative A12 A21 times x1 minus A12. I left off my x2 here, didn't I? Sorry about that. It's A12 times A22 times x2, and that would be equal to the minus of A12 B2. Okay, now why would we do that? They told us to. No, the reason we did it is that this term and this term are exactly the same but with opposite signs, right? So therefore when you add these two together, these disappear and you get A11 A22 minus A12 A21 times x sub 1 is equal to A22 B1 minus A12 B2. Whew. All right, now divide both sides by this thing right here. So that goes away here, and it winds up over here as A11 A22 minus A12 A21. Now, I don't want to do all this again, but I want you to imagine doing it all again. But this time we're multiplying the top equation by let me think, get the signs right. By A yeah, let me write it down. Okay, it would be, this time we're trying to eliminate these, So you'll multiply by A21. I think we'll multiply by minus A21, the top equation, A11 x1 plus A12 x2 equal B1, and multiply the bottom equation by positive A11. Yeah. Okay. Not easy writing on the screen. Okay. Okay. And if you do that, you'll notice the first coefficient here will be A1 minus A11 A21, and down here you have a positive A11 A21. So that's going to add to 0. So what you have left here, and I'm going to skip steps here, x of 2, I'm just going to jump right to the chase here, like you have the x1 there, and what will it be? It will be A11 B2 minus A21 B1 divided by A11 A22 minus A12 A21, because that was the coefficient you have here left over. Okay, so it'd be this times this minus this times that, which we have in the numerator, divided by because these are going away, A11 A22 minus A21 A12, whichever order you do them. Now, what's the purpose of all this? Notice at what the denominators are in both cases. This denominator is exactly the same as this one. A11 A21, A11 A22 minus A12 A21. Now, something else I want you to notice. What if we would have written this as A11 A12 A21 A22, that coefficient matrix times the variable vector x1 x2 is equal to the constant vector b1 b2. Okay, now what I want you to notice, that denominator over here, right here, these common denominators here, this is simply your determinant of this, A11 A22 minus A12 A21. I don't know what these noises are, but they're making noises. Okay, so basically we've got that the x sub 1, the solution for this matrix here, is something over the determinant of your coefficient matrix. And the x sub 2 here is something over the determinant of your coefficient matrix. Okay? Now, we've got that part figured out. Let's go back and see what those numerators are. Well, I want to notice what is similar here. The A22s are in both of these, and the A12s are in both of these. So what is different here is that instead of the A11 here, you put a B1, and instead of the A12 here, you put a B2. What are those? A21, I'm sorry. Instead of A21, you put a B2. What are those? A11 and A21, they are simply the coefficients. If I can get the pen, where is it? There it is. These are these coefficients here, which are the coefficients of x1, which is what you're looking for. And in their place, we put the constants. Okay? Now they're going to give a name for that. They're going to call that the determinant of a sub 1. I'll define what a sub 1 is for you, and similarly this coefficient here, the a11 and a21, they're okay here. What the b1 replaced was a12, which was the first coefficient of x2, and what the b2 replaced here was a22, which was the second coefficient of your x2, okay, in the original problem, okay? So your b's replace that. So this they're going to name determinant of a2. Now, I don't know what the beep is, okay? What is this a1? Okay, if I can get the pen to come down here and write. This a1 is simply the matrix that you get by replacing for x1 its coefficients, which is a11 a2 by b1 b2, and then leaving the a12 and the a22 alone. That's what the determinant of a1 is. a22 b1, where is it? Ah, there it is. a22 b1 minus a12 b2. Okay. Similarly, this a determinant of a2 will be the determinant of the coefficients, the constants replacing the coefficients of x2. So leave the x1 constants alone, a11 and a21, leave those alone, and instead of your coefficients of x2, we put in b1 and b2. All right, I'm drying up again. Let me give me a swig of something. Sorry about that. Okay, now let's check that out and see. This would be a11b2 minus a21b1. a11b2 minus a21b1. That's it exactly. So this is what Kramer's rule says. That determinant form of a solution is called Kramer's rule. Now they've done it for 2x2s. They've not made a claim about 3x3s or higher yet, but let's see if we can get there. Let's first deal with a 2x2. So let's go up here and clear the drawings, okay? And let's do an actual system of equations. 4x1 minus 2x2 is equal to 10, and 3x1 minus 5x2 That's supposed to be a 5. That is one of the ugliest 5s I've ever seen in my life. Okay, the pen is just not agreeing to write very well. Okay, let's try it again. 5x2 is equal to, I think it's 11, isn't it? Yeah. Okay. Now Cramer's rule says that we can write down our solutions like this. X sub 1 is equal to the determinant of your coefficient the denominator is the determinant of the coefficient matrix. So that would be the determinant of 4 minus 2, 3 minus 5. Okay? The numerator coefficient was put in your constants in place of the coefficients of x1, because that's what you're trying to get, and that would be 10, 11, negative 2, negative 5. Now, it looks like some pretty big numbers coming up here to me, so let's see what we've got. Let's do this first determinant. Okay. This will be minus 50, and then this would be, which would be plus 22, right? And that's divided by, the determinant here would be plus 6. Okay, now that looks like to me it would be a yuck. Okay, it's going to disappear in a minute. Okay, did y'all see that thing that happened, or is it just me? Oh, okay. It messes up my board and I can't write. Okay, this will be a negative 28, agreed, and this will be a negative 14. And that comes up to be what? Positive 2. Okay, the x sub 2, we don't need to do nearly as much work, if I could get my pen to stay a pen, because the denominator is exactly the same thing, negative 14. No reason to go back and redo it. That's the denominator, is the determinant of your coefficient matrix. But the new matrix here will be the determinant of your x1 coordinates as written, 4, 3, and now put 10, 11 in for your coefficients of your second, your x sub 2, and let's do that one. 44 over negative 14, and this would be 14 over negative 14 would equal to negative 1. Yeah, I did it again. Sorry. All right. We just solved that system of equation. Now, was that any easier than elimination by addition? Not much. I would say it probably was a little more involved, okay? Or by Gauss-Jordan elimination or Gauss elimination or something else? No, not that much easier either. But it's one way to solve a system of equations. And it's something that's fairly easily programmable, okay? If you think about the combinations are always there. So it certainly works. Oh, let's go back and check it. Let's plug in x1 equal 2 and x2 equal negative 1. So this would be 8 minus plus 2. That's equal to 10. That certainly works. And plug in that same. and you get us 3 plus 5 equal 11. Yep, that works, both instances. So there is your one and only one solution. Negative 2, negative 1. Okay, x1 equal 2, x2 equal negative 1. Now, the next part gets into 3x3s. Okay, so let me go on and clear our drawings here. And boy, these are a pain to write. Okay, but let's write it. A11 x sub 1 plus A12 x sub 2 plus A13 x sub 3 is equal to B1. A21 x sub 1 plus A22 x sub 2 plus A23 x sub 3 is equal to B2. Alright, excuse me just a moment. I'm getting dry again. Sorry. Alright, third one. A31 x sub 1 plus A32 x sub 2 plus A33 x sub 3 is equal to B3. Now, if you can extend the 2x2 rule to the 3x3 to make a 3x3 rule, then supposedly this would be your solution. Okay, your x sub 1 would be the determinant of, now instead of your coefficients for your x sub 1 that are here, we write in the b's. Okay, so that would be, the pen is just doing whatever it wants to. It's not paying any attention to what I'm doing. It's just drawing little squibbles all over the place. Okay, let's see if we can get it to calm down here. No, it's not. Look at that. I'm not even touching the screen and it's writing. I don't know what its problem is here. Okay, let's come down and try it again. This will be a B1 here, a B2 here, and a B3 here. And we'll write in the coefficients of the rest of them. A12, A22, A32. That's supposed to be a 3 there. That's worse. Now, I don't know why control is saying there. Okay, A13, A23, A33. Aha! That's your numerator. The denominator, let's just write it down as D. Let me write down what D is. D is equal to the determinant of, yuck, it's going to disappear in a minute, A11, A12, A13, A21, A22, A23, A31, A32, A33. All right. Okay, this is about the point where I'm getting so hungry I can hardly think. Okay, that is your determinant of your coefficient matrix. That is your denominator. Okay, so rather than write it down every time, I'm just going to write D. Okay, your x sub 2 is going to be the determinant of, this will be A11, A12, A21, A231, I keep saying it wrong, and then put your B's in here, B1, B2, and B3, and then put the coefficients of C in there of the third variable, A13, A23, A33. And that's over that same denominator D. The determinant of your coefficient matrix. And then A sub, or x sub 3, the solution. You just write down the solution basically. You have to do determinants and stuff. Okay, the numerator determinant would be A11, A21, A31. I found out if I write a little bit slower, it doesn't goof up as badly. A21, no, 1, 2, A22, and A23, and then you put your B's in for the coefficients for that, B1, B2, and B3. Gonna say something? Oh yeah, I'm sorry. Thank you. I've got to find my eraser. There it is. Three, 2. Okay, got it. All over that same denominator. Okay. So it's one way to solve a 3 by 3 without doing Gauss-Jordan elimination. But doing all these determinants, that's longer than doing a Gauss-Jordan elimination. However, this is something that's programmable, that you could do, program a computer to do it, and it would get done. Okay, so just another application of your a use of a determinant. Okay, application of the use of a determinant. Okay, so let's do one, example 4, which is going to be using Cramer's rule on a 3 by 3, and we will move from there. So let me erase the screen. Well, it's easier to erase with my finger here. Okay, now, but easier to write with the stylus. Now, by the way, you can go to larsonlinearalgebra.com and see an interactive version of this type of an example. Okay, so here is your system of equations. A minus x plus 2y minus 3z is equal to 1. A 2x, no y, plus z is equal to 0 and a 3x minus 4y plus 4z is equal to, I think it's a minus 1, isn't it? No, a 2. Okay. There's our system of equations. All right. If I want to solve that, which I do, okay, using Cramer's rule, which I don't particularly, but I'm going to do it because that's what they want us to do here. Of course, one of the first things we want to do is find out what that denominator is. And the denominator is the determinant of the coefficient matrix. Minus 1, 2, negative 3. And if I'm guessing what James is going to say, he'll say expand it. Minus 1, 2. Okay? 2, 0, 1, 2, 0. 3 minus 4 plus 4, 3 minus 4. Okay, now that's not really a determinant, but we're going to do our diagonals. Okay? If I can get the pen over here to write the equal sign. What's the first term going to be? First main down diagonal, 0. Second one, 6. Third one, you're right, plus 24. Okay, let me erase those because they're ugly. But I hope no one erases me because I'm ugly. But I am. Okay, now let's do the down diagonals. Up diagonals. First one's going to be a, next one's going to be a minus 4, and the third one's going to be a minus 16. Okay. I'm sorry. I don't know what brought that on. Okay. Now, easy way to do this in my mind is minus 16 minus 4 is minus 20 plus 24 plus 4 plus 6 is 10. All right. Now, that's what we got as our denominator. Now we just got to do 3 more determinants and we'll have the answer. Okay. So the x1 is going to be, when you plug in the 1, 0, 2, the constants for your x1 coefficients, and then plug in your 2, 0, minus 4. I don't know why the 4 is not working today. Okay, minus 4. And then plug in a minus 3, 1, 4. Repeat the first two, 1, 0, 2, and a 2, 0, negative 4. Now, I'm beginning to, I think I don't want to do this. I don't know why I was so slow to notice. But this is a pretty easy determinant to do. Right? this is all going to be over 10. That determinant, if we just use that second row there, right, it's going to be easy. First thing we ask ourselves, what's the sign of this position? It's a minus position. Okay, and we'll wipe out that row and that column and put a -1 there, times the determinant of what's left, and what would that be? 0. I don't know, is it? -8. Okay, it sounds like a 0, but okay, -8. Right, and that will be over 10, and that will be a positive 8 over 10, which is 4/5. There's your x1. How'd the book do so far? Yeah, they got it right. Actually, it's not x1, it's x, y, and z. So this is just an x here, not an x1. Okay. Let's do the y's next, if we can. Okay. The example in the book was said solve the systems for x. We just did. The y's are not that bad either. Okay. What the y would be? Okay. Yeah. -1, 2, 3. 0, 2 in the middle, and now do you want to expand this one or do something else? It's up to you. Okay, let's just expand this since we're here. -1, 2, 3, 1, 0, 2. Okay, we know what the denominator is, 10. Okay, so let's do our down diagonals, and you get a 0 for the first one, 3 for the next one, I think it's a -12, isn't it? Okay, -12. Now let's do the up diagonals. 0, which is +2, and then the last one is -8. Alright, let's see what that comes to. -20 plus 5 would be a -15 over 10. I can't find my pen. There it is. -15 over 10 is -3/2. Okay, the book didn't do that, so I can't check it, but I feel very confident that we got it right, don't you? Oh yeah, the book did do it too. -3/2. Now the only problem is I don't have very much room for z, so I'm going to try to squeeze it in maybe down here. Okay, let's see what we can squeeze here. Z is equal to, its numerator determinant is going to be the 1, 2, or -1, 2, 3, 2, 0, -4, right? And then a 1, 0, 2. And that's divided by 10. Okay. Goodness gracious. I'm running out of blood sugar fast. The gut is saying, feed me, but that's what it usually says. Okay, So this is going to be, I think, easier to do if we do our, is that what you mean? Okay. Now, what's the sign of that position there for where this 2 is? Okay, so it's going to be a -2 times the determinant of what's left. And what is that? Try again. Okay. Okay. Over 10, which would be -16 tenths, which is -8 fifths. And that's what the book got to. All right. So, you know, I think Gauss-Jordan is still the easiest way to go, but this is another way to do it. And it's relatively easy, I think, to program if you're programming. So we got our solution set to be x1 equal 4/5, x2 -3/2, and x3 equal, x equal 4/5, y is equal to -3/2, and z is equal to -8/5. Good deal. That was example 4. All right, so there's a second example of an application of a determinant. You can find an inverse by using the adjoint, which uses a determinant. You can use Cramer's rule to solve systems of equations, no matter how big or small, it'll work. Okay, and here comes another series of things. Now, this is a whole bunch of them, but they're all related in some sense or another. Let me get this out of the way and just use my finger to clear. It's a little faster. And this is finding areas, volumes, and equations of lines and equations of planes. Wow. Okay. Now, and here's their lead-in. Determinants have many applications in analytic geometry. Now, what do we mean by that? Is analyzing geometric things using algebraic things, okay, including linear algebraic things, okay. One application is finding the area of a triangle in the XY plane, okay. So let's say we have a triangle, and that triangle has 3 coordinates, 3 vertices. Of course it does. Triangles have that. X1, Y1, because they're in the XY plane. There's one vertex. The next vertex is X2, Y2. The next vertex is X3, Y3. Okay, that will form a triangle. Now, that forms a triangle as long as x1, x2, and x3 are not all on a straight line. And y1, y2, and y3 are not collinear. Okay? If either of those were the case, that's not going to be a triangle. But if x1's up here, xy's over here, x2's over, point 2's over here, like this, and point 3's down here, none of those are collinear in any way, shape, or form, then you've got a triangle. Okay? Now, here's what the area of that triangle is, believe it or not. Okay? If I can get it to write, the area of that triangle is going to be, now, it starts off strangely here. And the strangeness is you got a plus or a minus here. And it's really not as strange as what you might think, but it's 1/2 the determinant of 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 1/2 the determin x1, y1, 1, x2, y2, 1, x3, y3, 1. That determinant. Okay? Unbelievable that that would be a determinant like that. The third column always ones. Now, the 1/2, yet another mystery why that's there, but the plus or minus isn't really all that mysterious, and here's why. It may be the strangest thing to you. That determinant may be positive. If it is, you use the plus. But if that determinant happens to be a negative number, which it certainly could be, then you have to use the minus. Why? Areas are never negative. Never negative. So that's why they put the plus or minus in front. So you'll guarantee your answer is going to be positive. Okay? Now, they have a little proof for this, which is really a nice little geometric proof. Okay? And I don't know, we got plenty of time to do it, but I just don't know if we want to do it. Let's just draw our coordinate plane here, if I can find the pen to do so. Come on, pen. Oh, I wasn't holding it over the Wacom. Okay, here we go. So let's put the y-axis here and the x-axis here. Now those are supposed to be straight lines. They're not, obviously. Okay. Now let's just pick 3 points. So we're going to be in the first quadrant. It will work in other quadrants. Okay. 3 non-collinear points. Okay. And you want to call this point 1, point 2, and point, well, let's see how the book does it. Yeah, that's how they did it. And point 3 up here. Okay. So this value right here is x sub 1. This value over here is y sub 1. This value down here is x sub 2. And this value right here is y sub 2. And this value down here let's just call that, yuck, x sub 3, and the value up here we'll call y sub 3. Yeah, did it again. Okay. Now, that forms a triangle. Now, this is going to be, I'm going to use a cheater aid here to help me draw. I should have done the coordinate lines this way too, but I didn't. So, this is such a pain in the neck. Okay. Okay, there's a triangle. And what we're looking for here, come on, pen, show up there. Okay, is the area of that triangle. Now, what color you want the area of the triangle to be? Name a color. One of those colors. Can you see the colors?
No, sir.
Oh, you can't. Well, pick a color. Blue. I've got a very light blue, a Carolina blue, and a darker blue. Light blue. Okay. So that's going to be I'm just going to, can you see that? It's not drawing in very well. That's the area of the triangle we're interested in. Okay. Now, we're going to draw a couple more construction lines here. Okay. All right. The first of these, I'm going to try to draw as vertical as possible from here to there. Oh, let me get my color black to be black again. Okay, let's just imagine that could be a perpendicular line. Let's imagine this could be a perpendicular line. I probably should have done these first. And imagine this to be a vertical line. They're not quite vertical, but you get the general gist. Okay? Now, here's what we're going to do. Give me another color. Red, okay? There's a red. Okay, we're going to consider the area under this trapezoid here, because those are supposed to be vertical lines there. Okay, give me another color. Purple. Okay, best I've got is a lavender purple, so we'll do that one. Okay, so we got this trapezoid over here, right? Okay, and we got, give me one more color. Green. I've got a very pale green, a bright green, and a dark green. Bright. Okay, so that will be this one down here. Okay, now the area of a trapezoid, let's start with the red trapezoid. Okay, the red trapezoid here, the area of that red trapezoid, and this is trapezoid, TRA. If you remember what that is the, I'm going to draw another couple construction lines here, maybe to help you see what the area is. Okay. This is a pain in the neck. Okay, let's just imagine. Why did it stop there? Let's see if I can select. Okay. Okay, that's supposed to be a vertical line. That's supposed to be a vertical line, and that's supposed to be a horizontal line. Now, here's what I want you to imagine for me. Okay? Doesn't it appear to you to be that, here's what I was trying to do. I was trying to make this length here equal to this length here, and this length here to be equal to this length down here. Did I come relatively close to doing it? If I did, then don't you see that this and this are the same areas, right? If Okay, and they form a little rectangle here, don't they? The area of that rectangle would be the rectangle would be x3 minus x1, that's the length of the base, times the length of the height, which would be, let's say again, yes, y3 would certainly be in there. Y3 plus y1, right, plus y1, right? That's the height of this is y1, and this height right here, I can't get my pen to move, there it is, that height is the same as this, which is y3. So that's the area of the rectangle, and then divide it by 2, and that's the area of the red trapezoid. Okay, you buy that? Now let's do the lavender trapezoid, the purple. If I can get my pen to locate itself, there it is. The area of the lavender trapezoid, okay, is equal to, and it would be, extend the pen, okay, yeah, extend this line up here to be y2 height here, come on across here, and there's x2 minus x3, and then come down here, that height here would be your y3. So basically that would then be x2 minus x3, there's your base, times the sum of y2 plus y3, and that's divided by 2. Now that gives you those two. Now we have to subtract from that the last trapezoid. I need one more color. Want me to use brown? That's sort of different. I got brown, orange, and yellow. Choose one. Huh? Second? Brown will do. Okay. Now I hit the button again. Still didn't go off. There we go. Okay. The brown is going to be here. That trapezoid. You see that one? Okay. Now, the area of this brown trapezoid is going to be x2 minus x1, that's the base, and the height of that trapezoid is y1 plus y2. You see that? And that's divided by 2. Okay? Now, this is where things get, I'm not going to write all these out because it's a pain in the neck to do. What was our blue here? Was that the bright? That was the light blue. Okay. That's the area we're interested in. The area of the light blue here. Trapezoid. No, that's a triangle. That's the area of the triangle. This is a TRI as opposed to TRA. The area of the triangle, little blue area, is not that the area of the red trapezoid plus the area of the lavender trapezoid plus, oh, minus, sorry. Minus the area of the brown trapezoid. I trapped that one. Okay. Is that not the area? Area of red plus area of violet, that gives you the two big trapezoids there, minus the area of the one that's underneath the triangle. Subtract that off and you get the area of the triangle, the blue area of the triangle. Can you see that? I know it's sort of messy. Okay, and how in the world, I thought I just went in there and erased it and somehow it showed back up again. I don't know if I did that. Well, that is a minus. I thought I did that before, but it came back. Okay, the area of the red plus the area of the lavender minus the area of the brown gives you the area of the triangle. Now, and something else I can't see here is I've got my numerators there, and I forgot to write in a 2 here and a 2 there. That should be a lavender 2, but I'm not going to mess with it. So now, do you see where at least the 1/2 came from? Because every one of these areas has a 1/2 in front of it. So that's where the area comes, the 1/2 comes from. The plus or minus, because we know determinants could be positive or negative, but areas are always positive, so we use that. Now, if we were to, and I'm not about to, the book does it, do your foiling of this times this, plus this times that, plus this times this, plus this times that. I mean, do all of your foilings here and do them out. What you would find out when you ultimately get everything done, you have some pluses, some minuses, equal number pluses and minuses, and guess what? They're exactly the same products as you would have when you were doing your matrices. And that's what the book does, which I don't even come close to having time to do. Okay, but they write them all out there. Some of them cancel out and do different things, but they come out being exactly the products. And you see this one over here, there it is, the ones here, that means every time you do an extension of these, I mean, if you had expanded this thing, then when you do your down diagonal, say, it's just x1 times y2, right, times 1, and next would be a y1 times 1 times x3, you know, the next one would be a 1 times x2 times a y3. You come out with just pairs of numbers, because the 1 is the third number that you would have in there, and they turn out being exactly what your expansion would be with the correct signs. Of course, if those signs come out being negative, you use the minus in the front to make it positive. If they come out being positive, you do that. So much of that blah blah blah. Let's do example 5. Do we have time? I think, oh yes. All right, to do example 5, I think it's way easier to do it there rather than trying to fiddle around with the proof. Okay? So here's example 5. Find the area of the triangle whose vertices are, I'm still in brown, let me get back to black. Okay, 1, 1, 2, 2, and 4, 3. Okay, now I know right off the top those are not collinear, because the line that goes through 1, 1 and 2, 2 is your 45, and to get to 4, 3 you have to deviate. So yeah, that's going to be, in fact it deviates downward a little bit, so that's going to be a very thin triangle. So I don't anticipate being a very large area. Let's see what area we get. The area of this triangle then would be the determinant, or I'm sorry, let me not forget the most, not the most important, but an important feature here. For some reason the eraser's not coming on. Okay. All right. It's plus or minus 1/2 times the determinant of what? Is that right? Yeah. Well, x of 1 and y sub 1 are 1 and 1, right? Okay. He's trying to be difficult to me, aren't you? Okay. Next would be, which is, right? Next would be, right. Now we've been in the first quadrant only, and we still are, but this will work no matter what quadrant you're in, okay? We haven't done there. Now, since there's no zeros here, I say your best method here would be to repeat the first 2 columns, which is 1, 2, 4, and 1, 2, 3. Okay, now I'm going to do it as if that's a determinant, but you got what I'm doing is, this is going to be, don't forget your plus or minus 1/2 times, first entry here, next down diagonal, next down diagonal, plus 6. Okay, let me get my eraser. I don't have to erase these, but it just makes for easier reading if they're not in the way. Okay, whoops, the draw did not pick up. Okay, what would that be? Minus 8, minus 3, and minus 2. Okay, now I'm going to do the easy as I can. Wipe out the plus and minus 2. They add to 0. And your pluses add to 10, and your, well, I said I was wiping out the 2, and it suddenly disappeared. And I can't get my pen back. Where, oh, where has my pen go? There it is. Okay. Okay. Add the pluses together, you get a plus 10. Add the minuses together, you get a minus 1, right? So that's going to be a minus 11. And plus 10 minus 11 is minus 1 times, and which sign do you think we're going to use? No, the minus, because you want this to be positive. So your area, I said I thought it was going to be a pretty small area. The area is just 1/2. Okay, whatever your units were there, 1/2 square unit. Very small, because that was a very thin triangle. Very thin triangle. They did, well, they sort of showed a picture of it, but not quite. Okay. Now, so that's how you find the area of a triangle. Write down the coordinates in the matrix with the third column being a 1. Now this is a planar triangle, okay? Area of a triangle in the XY plane. If you're in space, don't try it, okay? We're going to get to that a little bit later, what you can do in space. But you can't find the area of a triangle in space with 3 vertices, with 3 coordinate axes. That is really difficult, okay? You can't do it using this. But this is in a plane where all you have is XY, then you put the 1 as the third entry and take the determinant. Now, like I said before, if these 3 points were collinear, it's not going to work because you have a 0 area. Well, if this is a plus or minus, which is not 0, and that's a 1/2, which is not 0, in order for a collinear, this had better turn out being the determinant. It better come out being 0. And indeed it does. Okay? Now I said if you had the point 3, 3, you know those are collinear. Also, if you'd had the first point being 0, 1, then you see your x is going up by 2 every time, your y is going up by 1 every time. So those are 3 collinear points. Okay? Well, let's see what happens to that if we had put those in. If we had had a 0, 1 rather than a 1, 1. The other 2 points the same. And here's what would have happened to us then. This would have been a 0 here, and that would have been a 0 there. Okay? And let's do the area then. What would you get? We know what we'd better get. Better get a 0. This is supposed to be a plus or minus 2, 1/2 here. Okay? Well, let's see what we get. That would be a 0. That would be a 4. So I don't need the vertical line there. Okay. Goodness, I'm getting hungry. Okay. That first one would have been a 4. And the next one would have been a plus 6, right? Okay. Then the first up diagonal would have been a minus 8. And then a 0, right? And then a minus 2. And guess what you get? 0 every day. Okay. So what you got, if you have 3 collinear points, the determinant has got to be 0. Now, that leads to another possibility. So what I'm going to do is clear my screen here, and using that principle that we just said, if you have 3 collinear points, the determinant is going to be 0. Well, what if you had 2 points? Of course, they've got to be collinear, and your third point was a variable x, y, okay? And you want to find the equation of that line. So, I jumped something. 3 points, x1, y1, x2. I left this out. Basically, we've already done it, but I do need to write it in. Whoops. My microphone thing fell off my pocket. Okay. If you have 3 points here, x1, y1, x2, y2, in a plane, they've got to be in a plane, and x3, y3, All right. Now, if you do what we just did, except leave off the other, all you do now is, if you're trying to find out if those are collinear or not, all you do is take the determinant of x1, y1, 1, x2, y2, 1, and x3, y3, 1. Take the determinant of that, see what you get. If it comes up any number in the world except 0, these are not collinear points. But if it comes up being 0, if that determinant is 0, then the implication of that is that they are collinear. They all land on the same line. Okay, that's if and only if. So they're collinear if and only if the determinant is 0. If the determinant is 0, they're collinear. Okay, now, not going to do anything else with that, but if you were doing your other thing, they came up with a determinant of 0, say, whoops, no area of a triangle, these are collinear points. Now, what I was starting to say before is, therefore, if we have 2 points, okay, 2 points, and you want the equation of the line between those 2 points, of course we could use the point slope formula. Of course you have to calculate the slope first and then do the other, or you could use what we just sort of discovered here and say this. If you have the situation that you have just 2 points, x1, y1, and x2, y2, and you want to find the equation of the line, what you do is write what we just said down, that the determinant of, but this time, unfortunately, I always write it on top, and I think it's okay to write it anywhere you want to, but they do it on top, so I'm going to do it on top. X, Y, 1. Here, X and Y are variables. To get an equation of a line, you got to have variables, okay? So those are your variables, and then your next 2 points, you put those in. X1, Y1, 1, and X2, Y2, 1. And you know if these are if you're trying to get an equation of a line, that determinant has to be 0. So we solved that. Okay, now I'm going to erase what I just wrote, if I can get the pen over here to erase. Okay, and expand. X, x1, x2, y, y1, y2. And then do this. And what we get there is, now remember, the x1, x2, y1, y2, those are numbers. Those are coordinates for a point. So here's what we have is, the down diagonal here is just y1 x plus x2y plus x1 y1 yuck x1 y1 wait a minute yuck okay. I'm getting tired, frustrated, and hungry. Okay. That was my third one, plus, except it's y2. Y'all are letting me get away with all sorts of mess today. X1, Y2, right? Minus X1, X2, Y1 minus Y2, X minus X1Y. Now I did it without drawing the lines. Would it be helpful to draw the lines? You tell me. My construction lines. Did you see where I got those numbers and things? Okay, so let's put this all together. What we have is Y1 minus Y2 times X plus X2 minus Y2, no, minus X1. Let me erase all that. Is equal to, I'm writing it like this, X2 Y1 minus X1 Y2. Okay, goodness gracious. You know, they didn't write any of that out. They just said the determinant's equal to 0. And set all this equal to 0. They didn't write it all out. Well, that's not quite true. You have to, I'm sorry, put the minus sign back in here and the plus sign here, and that's equal to 0. And then, well, I was doing that. I always said it equals 0. I moved it to the other side. So what I said was true, except I left off the y right here. Okay. They didn't go that far, and maybe for obvious reasons. It wasn't necessary. So I'm going to clear this, and let's do we have time? Yeah, I think we have time to do example 6. All that was much harder than doing the actual problem. Here are the 2 points that we're interested in, 2, 4, and -1, 3. Okay, now we're no longer in the first quadrant only anymore, and that's perfectly fine. All right, we want the equation of a line passing through those 2 points. Well, let's see. That would be, you set up your determinant, and they usually do x, y, 1 in the top, 2, 4, 1 in the second, and -1, 3, 1 in the third, and set that equal to 0. Okay. All right. Let's do our first down diagonal. I'll draw them this time. Okay. That would say 4x, right? Oh, I forgot to expand. Okay. X to -1, y 4, 3. Okay. So and that's equal to 0. So this produces 4x. Oh! All right. Plus or minus y plus 6. Okay, that would be a plus 4, right? Minus 3x and second minus 2y. You got it, minus 2y. Okay, and what does this give us? X minus 3y plus 10 is equal to 0, or x minus 3y is equal to negative 10. I don't know which way they did it. Yep, they said x minus 3y is equal to negative 10. Perfect. All right, so that was example 6. Now, I don't know if you remember back in one of the last sections or two, there was a little blurb at the bottom of the page about the volume of tetrahedron, and it said we're going to get to doing that, and that's the application of a determinant. Well, now we're running into that. Now, what a tetrahedron is a four-sided figure in space. So you have x1, y1, and z1, x, y, and z coordinates. So 4 points in space, all connected by a line between every one of the pairs of points. Okay, and as long as those 4 points are not coplanar, okay, all 4 in the same plane, you'll form a tetrahedron. Okay, and let's at least hit the theory of it here. The volume of a tetrahedron with 4 points in space, x1, y1, z1, you're in space, so you're three-dimensional, x2, y2, z2, x3, y3, z3, and the fourth point, x sub 4, y sub 4, z sub 4. Goodness gracious. Okay, now the volume of that tetrahedron, everything's a T today, it seems like. The volume of that tetrahedron, I'll call it a TE for tetrahedron, is equal to, guess what, we got another plus or minus, because volumes have to be positive. Now, it's no longer 1/2. The coefficient here is now 1/6. The determinant from, I think you could probably guess, x sub 1, y sub 1, z sub 1, 1. X sub 2, y sub 2, z sub 2, 1. X sub 3, y sub 3, z sub 3, 1. X sub 4, y sub 4, z sub 4, 1. That determinant, 4 by 4s, aren't they fun? That would give you 1/6 of that determinant, plus or minus to make it positive, would give you the volume of that tetrahedron, as long as all 4 points are on the same plane. Okay, and we'll get to that a little bit later. So they give a picture in the book and ask you to calculate the volume of the tetrahedron. Okay, now we have 1 minute. I don't think that James will be able to finish that in a minute. He's awfully slow, you know. So let's pause there, and that's where we'll pick up next time. Somewhere here, once upon a time, I had an eraser and a pencil. There they are. They're hiding. Okay. So next time we'll pick up and do example 7, volume of tetrahedron, and same time, homework exercises. We came so close to finishing 3.4. Homework exercises here would be any of the odds 1 through 7. They're in the back of the book and at calcchat.com. Any of the odds 9 through 21, they're all at CalcChat, in the back of the book and at CalcChat. 23 and 25, they say, are a little bit tougher. They're bigger, okay, and they say you may need some a graphing utility to help, or a software program. So I'll let you decide. 23, I think you could do. It's got fractions, but you could do it. 25 does have a lot of zeros, so you still could do it, I think. Okay. 27, you could do that one. It should be at CalcChat also. 29 or 31, volumes of areas of triangles. Testing for collinear points, 33 or 35. And then 37 or 39, find the equation of a line. We'll stop there because we didn't actually do the example of the volume of a tetrahedron. So we'll finish those next time, and I'm pretty sure we will finish the chapter. So I'll try to have your test ready to go. I'll probably post it as soon as class is over on Thursday. Sound okay to you? And that way you'll have plenty of time this weekend to work on it. But you do have a whole week, of course, to do it, and longer if you need it. So that means start getting in those second tests if you haven't already done so, because here comes the third on Thursday. So try to get those in. All right, any last thoughts, parting shots, questions? Okay, well, I'll stop sharing because I'm tired of sharing with you guys. I'm going to end the recording here, or end the meeting here. And unless there's any other issues, I'll be ending it. So we'll see you on Thursday, and take care.